we would be talking about training large-scale models using PyTorch. I think the first question is, why should we care about training these large-scale models, right? Um, so why should we? I'm sure a bunch of you have used ChatGPT or Bard or Anthropic's Claude or are using Llama for doing some stuff. And all these are large-scale models. And given that these models are becoming so useful and so powerful, it's very useful to think about what takes it to train these kind of large-scale models. Uh, the other reason to think about or caring about training large-scale models is this following curve. This is from the neural scaling laws paper. What this shows is this is three different curves. On the x-axis, we have compute or the dataset size or the parameters, and on the y-axis, we have the test loss. That it's not important as to what the task is. The trend that we are seeing is as we increase compute, that is, as we move along the right side on the x-axis, or as we increase the size of the dataset, or as we increase the size of the models, we see a clear improvement in performance indicated by the lowering of the test loss. So this is basically to say that we care about large-scale models because large-scale models enable things. They have performance. They enable much better performance than smaller scale models. The other reason I like this image a lot is because this talks about different axes along which you can be scaling models. So one of the axes along which you scale a model is to train it with a lot of compute. The other axis is to train a model with a lot of data. And the third axis is to train a very big model, a model with a lot of parameters. So very often when we say we are training large scale models, people just assume that the model is too big, but there are these two other dimensions in terms of compute and in terms of data set size as well. And that's going to be the theme of this talk. We'll talk about some of the common problems that people run into when they are trying to scale models along these three axes and what are some of the ways that we can get around that using PyTorch. I also want to say that a bunch of non-agenda for this talk is we wouldn't talk about how to get a lot of training data and we wouldn't talk about how to get a lot of compute. We would also not talk about how to do good science. So this is in no way an exhaustive talk. This is basically, hey, these are the different things that you can do for training large-scale models in PyTorch, but it's not exhaustive. Okay, so what are some of the common challenges that we come across? The first challenge is that, hey, I have got a lot of data available, but my model is not too big. And when we say my model is not too big, it basically means that the model can fit on a single GPU. I've got data, I've got a model that fits on a GPU, but it takes a lot of time to finish iterating on the dataset, or it takes a lot of time to train the model on this dataset. So this is one of the common challenges that we get through. And this is a very classic systems problem. This problem can be reformulated as saying, I have got a workload that is running, but it's running too slow, and I want to make it go faster. And the way to do that is to parallelize the workload across a bunch of machines. And when we do it in machine learning, we call this thing as data parallel. Data parallel basically means that you are consuming the data in parallel across a bunch of machines. And in PyTorch, we specifically call it as distributed data parallel, where the first distributed basically means that you are doing data parallel across a bunch of machines. So, DP or DTP. Just to give you a sense of how that looks like, this is a single GPU setup. You've got a data set, you've got a model. We break the data set into batches. Let's say there are 4 batches here. And then the model starts consuming them. So at time step equal to 1, it consumes the first batch, then second batch, then third batch, and fourth batch. So it takes 4 steps to consume the entire data set. So this is a single GPU setup. Now, let's say I was in a multi-GPU setup where I had multiple GPUs and I was using distributed data parallel. What would happen is that I'll still have the same data set, I'll still have the same model, and I'll still break my data set into batches. So let's say there are still 4 batches. But now I would have 2 copies of the model, 1 copy running on each GPU. So if I had 2 GPUs, I'll have 2 copies. If I had 10 GPUs, I'll have 10 copies. And the benefit of having multiple copies of the model is now I can consume 2 batches at once instead of just 1 batch. So at time step t equal to 1, I have consumed batch 1 and batch 2. And at time step 2, I've consumed the remaining 2 batches. So instead of taking 4 steps to consume the batches, now I'm just taking 2 steps. And in that sense, it makes your training go faster because you're consuming batches faster. So that's the high-level overview of what distributed data parallel does. The broad idea is that you start multiple processes, one process per GPU. For each process, you initialize a process group. We wouldn't go into details of what a process group is, but basically the idea is that these processes need a way to communicate with each other. If you're doing this on CPU, you can use things like MPI, but if you're doing it on GPUs, then you need to use something called as Nickel. Nickel is Coda's communication library. Again, we don't have to go into those details. And the last thing is that you have to update your data loader to use a distributed sampler. This bit is needed to make sure when when these two copies of model are consuming a batch, they are consuming different batches and not consuming the exact same batch, because in that case, you're not going to see any speedups. And just to give you a quick example of what the code could look like for things like this, we have a world size, which is basically how many devices are we using. And we set up these DDP processes, which is basically just saying that, which is basically just providing a way for these processes to communicate. So we provide a master address and a master port. So all the processes are going to use this address and this port to communicate. And then we just initialize the process group. I think the only interesting thing here is this attribute called as backend equal to nickel. In CCL, it's pronounced as nickel. I think the thing to note is if you are doing distributed data parallel on GPUs, you should be using nickel NCCL. If you are doing distributed data parallel on CPUs, you should be using glue. And that's it. That's the main thing that you need to know if you want to start using distributed data parallel. Okay, so this is good. Just to re-summarize, what exactly did we do in this challenge is we took a workload which was running but was running slow, and we distributed it across multiple machines, and we call this as distributed data parallel. And one other way you can think about this problem is that you are making the process go faster by increasing the batch size, because now you're consuming 2 batches. So in a sense, your batch size is double now. One caveat to note here is that this way of making training go faster assumes that you have more GPUs, which may not be the case all the time, but it's good to know that caveat. Okay, let's talk about a different kind of challenge. In this case, I may have a lot of data, I may have very little data, but my model is too big. My model is so big that I cannot train even with a batch size of 1. Basically, I cannot do any training. Maybe my model is just too big to even fit on a GPU. Now, in a setup like this, distributed data parallel is not going to help me, because what distributed data parallel does is it allows me to increase the batch size. But for that, I should be able to load at least a batch size of 1. Whereas in this case, I cannot even do that. So distributed data parallel is out of the way. We have to think of something else. Well, this is another classical systems problem. So we have a workload that we want to run, but this workload is very, very large to run. And so the way we handle this problem is we shard the workload. Sharding basically means we distribute or we divide the workload across multiple machines. And in context of machine learning, we call it as model parallelism. I want to contrast it with data parallelism, where we had multiple copies of the model on different devices and the data was divided. In this case, the model is going to be divided across a bunch of machines. So what we'll do is we'll take a big model and we'll break it down into pieces. And these different pieces will be living on different machines. This is one example of what model parallelism could look like. So we have got these 8 blocks here. On the horizontal axis or on the x-axis, you have got time. And these different colors are denoting basically different machines. So you have got a model which is distributed across 4 machines. The F0, F0, F0s, F0s, these 4 F0s basically means that you had a batch of data which is going through these different machines. And F basically stands for a forward pass. It basically means you're computing the output of the model. So you take the model, you break it into 4 pieces. The first piece goes to the first machine. You take its output, you pass it to the second machine. You take its output, you pass it to the third machine. You take its output, you pass it to the fourth machine. And then the backward starts, which means you start computing the gradients. So you compute the gradients on the fourth machine, then you compute the gradient on the third machine, then on the second machine, then on the first machine. And then the update of the model parameters happens. Yeah. So in this way, you can break your model into as many sort of components as you like, or as many components as you can break it into, given the number of GPUs that you have, and you can pipeline, or you can sort of create this pipeline of processes happening. One obvious disadvantage of doing something like this is there's a lot of white space that you see here, right? And this is all white space when these machines are not really doing anything. So it wastes a lot of compute when the different machines are sitting idle. And so one other thing that you can do is called as pipeline parallelism, which is also a different form of model parallelism. The main difference with pipeline parallelism is you have multiple batches in pipeline. So again, let's try to interpret this plot. On the x-axis or in the horizontal side, you have got basically time ticking away. So you start with F00. F00 means that on the 0th machine, you've got the 0th batch. So at time step t equal to 0, you get that. And time step t equal to 1, you get a new batch on the 0th machine. But And so you get a new batch on the 0th machine, and you take the output from the previous batch and you pass it to the first machine. And then at time t equal to 2, you take the output from the first machine, you pass it to the second machine, you take the output from the 0th machine, you pass it to the first machine, and you put in a new batch into the first machine. So you're basically creating a pipeline. Uh, and the benefit of creating a pipeline is that the amount of wasted time or the idle time, which is the white space in this case, is reduced. But it's effectively doing the same kind of thing, but at a better throughput. And then you can do it in a more fancy way to reduce the overhead even more. So in this case, the uh, the white blocks with diagonal lines are the idle states, and you can see in this case then the percentage of idle state is actually much less. So you can do all these fancy sort of scheduling around these things. Uh, so PyTorch supports that. PyTorch supports that with this API called as pipeline parallelism, and it's relatively straightforward to use this API. So what you do is you create a pipe, and then you take your model. Now, instead of making a standard model, you make a sequential model so that it's easy for pipeline to break this model along different axes. So in this case, for example, let's say I'm making a 8-layer transformer. So modulus is going to be 8 elements. And I'm saying the size of the chunks is 8. So one chunk or one module would sit on one of the 8 machines. And then when I'm doing a forward pass, I do the forward pass as before, model.data. And then at the end, to get the value from the forward pass, I have to do this extra thing called as a dot local underscore value, which basically says, give me the value on this machine, on the specific machine where I call the output. But other than that, it composes pretty well with the existing constructs in PyTorch. Uh, okay. Um, Now, the good thing is if I have a model which I can load finally by dividing it across multiple machines, can I still increase the batch size with distributed data parallel? And it turns out yes. So you can do the exact same thing. First, make your model in a pipeline parallelism manner, make it so that it can load a decent batch size, and then you can increase that batch size by creating copies of this pipeline model. So this is another example which is showing this. So you've got a model, a torch or sequential model, let's say. You are putting it through a pipeline pipe, and you're breaking into a fixed number of chunks. And then this model that comes out, you are doing distributed data parallel over this model. So all this stuff around torch.nn.parallel, for distributed data parallel, this is all boilerplate stuff. And we just need the process group again, and we wrap this model with DDP. Uh, so it's pretty good that these two APIs compose well with each other. Okay, so now obviously fixing this challenge also assumes that you have enough GPUs and you can do these things. A third axis of challenge is my layers are so big that I cannot put one layer on a GPU. So again, focus on the axis in which we are going. So we said we have a model that fits on a GPU, but the data set is too big, distributed data parallel. Then we said the model is too big. So we said, okay, let's put one layer on a machine and then do training through it. And then you can combine data parallel through it. Now we are talking about a setup where even a single layer is too big to fit on a GPU. So pipeline parallelism is not going to help us here because pipeline parallelism assumes that you can put different layers across different GPUs. But in this case, I cannot even do that. So distributed data parallel doesn't work, model parallel doesn't work. What can I do? Again, this is similar to the previous classical systems problem that we have seen. We have a workload that is very large. And the way we solve this problem is by sharding the workload. And in this case, we call this approach as tensor parallelism. And what's the difference between tensor parallelism and model parallelism? Model parallelism was splitting a model vertically. So you had layers going across different machines. In this case, you're partitioning the model horizontally in the sense that you could have a layer, and that layer itself, a feed-forward layer or a linear layer, for example, is sharded across different GPUs. So even that layer is not on a single GPU. An example of this is shown here. So let's see what is it that we are trying to do. Let's say we are trying to compute the output y, which is GALU of x of a. So x is our input, a is our weight matrix, GALU is a nonlinearity. It's a pointwise nonlinearity. Think of it as ReLU, for example. So I get my input x. I break my input into, or I basically create two copies of my input, x and x. So I have two copies of my input. My weight matrix capital A has been sharded in two smaller matrices A1 and A2, and these smaller matrices are small enough that they can fit on a single GPU. So the entire matrix A was too big to fit on a GPU, but the smaller A1 and A2 can. So I first compute x of A1, on one machine, I compute x of a2 on the second machine, then I apply GALU. I can apply GALU this way because these are pointwise nonlinearities, and then I get y1 and y2, and then I can combine these y1 and y2. Or I could feed it through another tensor parallel layer. So let's say in the next operation, I wanted to, so with the y that I computed, I wanted to compute a y times v. V is another matrix. And I wanted to compute dropout on top of it. So in this case, I take y1, I take y2, and then I multiply y1 with b1, which is one of the shards of capital B matrix, and then multiply y2 by the other shard b2, complete the z1 and z2s, sort of combine them together, apply dropout, and get the final value that I care about. And again, in this case, B is a full matrix, but y1 b1 and y2 b2 could be lying on different machines. Yeah. And I also want to highlight that you may want to, for example, put A1 and B1 on the same machine. So you could do that. So in this case, you're sharding the model along the horizontal axis. Does PyTorch support that? Yes, to a good extent. It's somewhat of an experimental support. It's a relatively new thing that was added, but it does support that through these APIs like parallelize module or parallelize parallel and so on. And the high level idea is still the same. You define your model the usual way that you would, and then you pass it through this parallelized module construct, and it parallelizes the layers for you. But this support is experimental, so there are going to be some rough edges with this. Okay, and just like the previous setups, it assumes that you can have more GPUs, and so yeah. Now the fourth setup. The fourth setup is more of a sort of an umbrella term. So I basically want to reduce the memory consumption of my training setup, and this challenge is sort of orthogonal to everything else we discussed. So even if I have a lot of GPUs, I might still want to reduce the memory consumption of my training setup. So this applies to basically all the things that we saw so far. And there are these bunch of techniques for doing that. One of these techniques is called a CPU offloading. CPU offloading basically means that when you're training a model on a GPU, you offload the parameters or the gradients from GPU to CPU when you're not using them. So it frees up GPU memory for putting in more stuff into that. So CPU offloading is supported in PyTorch. The other thing is activation checkpointing, or as some people call it as activation decomputation or gradient checkpointing. The high level idea is when you do a forward pass, you save a bunch of extra information that you use during the backward pass, which you don't really need for the forward pass itself, but you use it, you keep it around so that you can use it during the backward pass. So activation checkpointing reduces that memory consumption by not saving these extra information during the forward pass. And when you need this information in the backward pass, you recompute it. So in that sense, it's trading off memory for time. It gives you more memory, but it also increases the time because you have to redo these computations. The third way people handle, and activation checkpointing is also supported in PyTorch. The third way people can handle these is by doing mixed precision training. So instead of using FP32, which is a 4-byte precision format, you can use FP16, which is a 2-byte precision format, or BF16, another 2-byte precision format, or TF32, which is a 19-byte format. And so that gives you roughly 50% memory saving right away. So mixed precision training is also supported in PyTorch. But let's say these things were not enough and I wanted to reduce the memory consumption even further. So then the question is, who exactly is consuming the memory? And well, the model state is going to consume some memory. Gradients are going to consume memory. And optimizer is going to consume some memory. And so are the activations. So all these things are things that consume the memory. So there's this technique called as fully sharded data parallel, where you shard the model state, gradients, and optimizers. And by sharding, we mean you have the model state, but the entire model state is not on one GPU. The model state is across a bunch of GPUs, and similarly, the gradients are not on one GPU, they're across a bunch of GPUs. And the optimizer is also broken down across a bunch of GPUs. So fully sharded data parallel, it's a form of data parallel, and it's called fully sharded because everything is sharded. The model state, the gradient, optimizer, everything is sharded. This is a high-level sort of overview of how FSDP works, but we wouldn't go into this here. The main thing to know here is FSDP is relatively straightforward to use with PyTorch. So you make your model, and then you wrap it into FSDP. And after wrapping up, you get a sharded module, and you use the sharded module to create the optimizer. And that's it. And then you keep doing your standard PyTorch stuff as you would do otherwise. Yeah, so I think this covers most of the things that are available out of the box for people to use for training large-scale models with PyTorch. if these things are not sufficient, or if you have a use case which isn't covered fully by these things, PyTorch also provides low-level APIs called as Torch Distributed. Torch Distributed basically provides communication primitives or a mechanism for the different GPUs or different machines to talk to each other. So, for example, when we are talking about, this model has been broken down across machines, and these outputs are flowing through those machines. The way you are doing this is, for example, using torch.distributed.send. So you can say, hey, GPU1 should send its activations or its results to GPU2, or GPU2 should pull the results from GPU1 and things like those. So those low-level APIs are also exposed, and you can use those to build a different kind of solution if the existing solutions do not already work for you. And in terms of the communication primitives, you have point-to-point communication. So one GPU can talk to the other GPU. You can have collective operations where a group of GPUs are sort of doing some collective operations like broadcasting or reducing. Now all these things are very well documented on the PyTorch docs, and Discuss forums are a great place to ask questions about PyTorch. Now, we discussed a bunch of things, but there's still a lot of things that we did not cover, which is very useful for training large-scale models. This includes things like distributed RPC. It includes things like distributed optimizers. Distributed RPC and distributed optimizers are basically alternative ways of distributing your workload. Distributed elastic basically is a way where, let's say you start training a model with 100 GPUs and one of the GPUs die in between. In that case, your entire model training would halt. But distributed elastic lets you continue the training when a subset of nodes die. And this is important because when you are training these models on, let's say, 1,000 GPUs, it is very likely that one or more GPUs could fail. And if that happens, a small percentage of GPUs failing should not bring down your entire training. So distributed elastic handles that for you out of the box. Okay, I think this is all I wanted to talk about. We have 4 more minutes left for questions. The slides would be uploaded at this link, so you can go and check out the slides there. And with that, I'll open it up for questions.
Do you also use a lot of PyTorch and scaling in the work that you're doing right now?
Yes, so for most part, we use FSDP. So far, we haven't really run into situations where we had to create something entirely new. So this is good because creating these things is debugging these things is super annoying. Creating is not that hard. But yes, most of our workloads run on FSDP. Pretty much all of it runs on FSDP.
Nice. I'm sure a lot of people would love to get a inside view on the stuff that you're doing.
Yeah, I don't think I can talk a lot about the exact thing that we are trying to build, but yeah. The high level idea is we are trying to train a bunch of multimodal foundation models. Multimodal in the sense that you have got multiple modalities that people can interact with, that people can use, and they should be able to use these things at the same time instead of. So one view is that you can train these independent models and just sort of fuse them together, and this is called as late fusion. Late fusion basically means you have these independent models and then you're combining their output. Early fusion means that you're training it in a multimodal way right from the start. So yeah, we are focusing somewhat more on that kind of a setup, but I don't think I can talk too much about the end use case that we're hoping to make.
Cool. Yeah, thank you again for talking about all the different considerations and ways to deal with large-scale machine learning.
Great, thank you for having me and for organizing this conference. It's exciting.